Hello, F Sharp. Welcome back. So today's gonna be a fun day. This is a good one. So this is a continuation from my previous video, and you saw, if you watched those, what I was trying to do is come up with a way for tracking an assignment, which is composed of a job ID, a machine ID, and an operation ID that was faster than HashSet, and specifically HashSet of Int64s. And we are deep we are deep into micro optimization territory. But I mean, this is the content that I have been able to find. So I wanted to share it with you because I figured this is for a future version of me who got into .NET and got excited about doing performance work. And there's this big chasm between the general guidance of use the right data structure, and then now you're programming in C. And so I'm trying to fill that in for the F# developer. And last time what we did is we had the HashSet, and we also had this new type that I had to find. And let me zoom in here for you just to make sure it's all nice and easy to read. And this was a BitSetTracker. And what it was using is just had an array of Int64s, unsigned Int64s, and I was really just treating that as a bit array that I was manually managing. And so I would take a job ID, a machine ID, and an operation ID, and the combination of those things would correspond to a single bit in this array. And the performance was much better. And if you remember, these first few lines are what the performance of the HashSet was, which is great. And we found that, hey, using this BitSetTracker idea, we were able to go dramatically faster. And I put out a tweet saying like, hey, I think this is really great, and I'd be really curious if someone could beat that. And fortunately, a person from the community did. His name is Mårten. It's Swedish, so if I mispronounce, my sincere apologies. I am very grateful for the help that you provided. But what he was able to find is that there is actually significantly more speed that can be found. And I wanted to dedicate an entire video into the optimizations that they provided that achieved this additional significant gain. And at this point, I know we're talking in nanoseconds, but this thing is running millions and millions of times. And so this additional performance is huge. And I was just like, whoa, where is this coming from? So I am really excited to unpack that for you. So BitSetTracker was the original idea, and it would take the job ID, the machine ID, and the operation ID. It would check that that was within the bounds of this tracker. So if you tried looking up something that was out of the original bounds, it would throw an error. And then what it did is it would compute the location, so the bit in this array that corresponds to that combination. It would then find the bucket, so which unsigned Int64 is this bit in, and then it would find, okay, which bit in that bucket is the one I'm interested in. In this case, it's adding it to the set. And in the remove method is doing the exact same math, but then it's setting that bit to 0. And then map is an algorithm for just quickly iterating through that array. So what we're going to cover is how to speed up these add and remove methods. So let's go down here and look at it. And we're going to come back to these details here. But what Mårten proposed was this inlining BitSetTracker. So conceptually the same thing, where when we create an instance, we give it the job count, the machine count, and the operation count, so it knows exactly how many bits it's going to need to use for tracking this. It computes the number of unsigned Int64s it's going to need, and it creates an array with that many unsigned Int64s. Next thing it does is it exposes all those values as properties. And as Mårten says here, these need to be public to support inlining. And we notice here that both of the methods, both add and remove, have been marked with inline. So this is one of the major performance improvements. Now, what is inlining? So whenever your code calls a method and you give it arguments, what it's doing is it creates a new stack frame with those values at the top of that frame. There's actually a great video by Scott Hanselman where he discusses what is a stack frame and what is it as compared to stack. I don't have enough time here to kind of unpack that, but there's a link down below. So if you're not familiar with what stack frames are, that's a really great thing to look at. What's important to know from a performance standpoint is every time you call a method or a function, it potentially could create a new stack frame. And when it creates that new stack frame, it needs to copy data to that stack frame so that that frame can then do the work that it needs to do. So here what you see, like these would be the values it would create a new stack frame, which is where the stack is. So when everyone talks about stack allocation or the stack, this is the data that they're talking about. It creates a stack frame. It copies this information into that stack frame so that it can use it, and then it performs these operations on top of that. Now, that copying is insanely fast, but it is not free. So one of the major optimizations that compilers will do is if a method is really small or a function is really small, what it will do is it say like, you know what? I know you're calling this new method or function, but instead of me creating a new stack frame for it, what I'm going to do is I'm going to take all that code and I'm going to inline it into where it's being called. And when you inline it, it's like basically taking all this code and putting it in the code where it's being called from. And what that means is now you don't need to create a new stack frame. That can provide huge speed ups. Now you don't want to do that infinitely. So there's debates on whether, like how far you want to go with that. But suffice to say, it's a major optimization because it reduces the amount, you don't have to copy arguments whenever you call a new stack frame with this inlining, which is really cool. And if you're working in C#, there's actually an attribute that you can put on methods to say, hey, aggressive inlining. And it's telling the CLR, like, I want you to try, I really, really, really would like it if you inline this method. And the CLR can decide whether it wants to do that or not. They can say like, whoa, no, this method is way too big. I am not going to do all that. So what will end up happening is that, sorry, I just need to check something here real quick. Yeah, I'm good. So the CLR can decide, you know what? I know you would like me to do it, but I'm not going to. F# is interesting in that it has this inline keyword and it's like a more powerful, it's no longer a suggestion to the compiler about like, I would like you to inline this method. This is saying you are going to inline this method, period. Now, don't go too nuts with this. Again, I would suggest before you start just throwing inline everywhere to say like, oh, it's going to make it faster. First of all, benchmark. It's not a get out of jail free card. And there are downsides to it in terms of just debugging and being able to put like breakpoints and go to them. I don't know if I'm doing something wrong, but whenever I start inlining stuff and I try to put a breakpoint there, I don't hit those breakpoints. So I might be doing something wrong, but there are downsides to inlining. Don't go too nuts. But what's important here is we've just discussed like, hey, inlining is this optimization. Compilers like to do it. In F#, we actually have a keyword. We can force it. There are some gotchas with it, though, that I want you to be aware of. So right now you see how Mårten made all these members, they're public. And when he computes this function, compute bucket and mask, which we'll get to in a second, he is not, they're not just using job count and this is referencing the argument from when this was constructed. Like you would think that would work. And right now the compiler is not complaining. But if you tried running this right now, we can go ahead and do it. I got to stop alt tabbing. So I'm going to go ahead and try to run the benchmark right now. And you're going to see the problem that this causes. It's saying, whoa, this value add was marked inline, but its implementation makes use of an internal or private function, which is not sufficiently accessible. That's confusing. What it's saying is that, hey, job count, machine count, and operation count are private to this class. Like you can use them inside of them, but they're private, which means it can't, when it tries to inline stuff, it can't do it. It doesn't have access to it. So that's why Mårten had to make these members public. And then instead of calling it this way by just using the value from the constructor, Mårten is using the instance here to say like, hey, use this job count. So that's one of those gotchas, because right now you see like nothing's complaining. I'm not getting any red squiggles saying like, hey, this doesn't compile. So that's something that can be confusing when you're using inlining, because like, wait a minute, why isn't this working? So inlining. And he also inlined this compute bucket and mask. So all of this code is being completely inlined. The call to compute bucket and masked is inlined here, and this call to add is also inlined into wherever it's called. So there's just inlining happening over the place. So instead of this creating a stack frame and this function creating a stack frame, there's no additional stack frames because they're being inlined. Okay, so there's that. That's really cool. Inlining is great. Let's talk about compute bucket and mask now. So something you'll notice that is different here is that instead of doing the comparison of job ID less than or equal to job count and greater than or equal to 0. So this is what this is up here. So here it's saying, hey, if this job ID is greater than the job count or it's less than 0, I'm going to give you an index out of range exception. So there's two different checks going on here. Down here, though, when we say, hey, treat this as an unsigned int, it's only having to do a single comparison instead of multiple comparisons. Why is that? So first of all, taking an int and then saying, hey, this is an unsigned int, that's free. There is no code that needs to run on the CPU to do that. So that is like a completely free thing to do. There's actually no work going on when you say, treat this as an unsigned int now. What does happen though, and this is interesting, if you have a negative number, a negative integer, that most significant bit is 1. It's going to be 1 to indicate zeroness. And it's okay, it's a little bit more complicated than that because of 2's complement. Like, I suggest looking into it. But the important thing is a negative number when cast to an unsigned int will be an extremely large number. Okay? And what that means is that if the job ID that comes in is negative, it will be extremely large. If the job ID is a positive number, it will stay that positive number. And so if it's a positive number that's outside the bounds, it will still be greater than or equal to job count. If it's a negative number, it will become extremely large and will also be much larger than job count. So what this is doing is whether it's a positive number that's outside the bounds or a negative number, it's still going to fail this check. So what this is doing is is it's reducing the number of comparisons that you're having to do. So this is just a fewer comparisons. So that speeds this up. It's small, but it's there. It's measurable. I've tried this with and without, and it ends up affording you about 2 nanoseconds, depending. So, which is like not that much, but still, when you're like going for as fast as possible, these things add up. So next thing here is very clever. And this comes to the fact that ints are stored in base 2, and that if you want to multiply and divide in base 2, you can just shift bits. So instead of actually having to multiply, you do a bit shift left or right. We also know that, okay, so we have this similar computation to get the location. We do some math, we do some multiplication and some addition. So nothing really changed here, but we're just computing which location of the bit that we're interested in. Now we need to get which int 64 we're interested in, which is the bucket. And we need the offset within that bucket to get to the bit that we want to know. Well, in this case that we're wanting to get. Instead of dividing by 64, which is expensive, we can do a bit shift of 6. And because it's base 2, that is equivalent. Now, why on earth would we do that? So one of my favorite resources on the internet is a website maintained by Agner Fogg, who is a developer who maintains incredible resources on optimizing for x86 architecture. And he has some PDFs which provide the timings for all the different instructions for the different CPUs. I am running a Zen 2 processor. And so I come into this and I go look up AMD Zen 2, and I can look at how long do all the different operations take for the CPU, because different CPUs will have different performance depending on it. And these are the instructions. So these are move instructions. We got some push instructions, some like lookups. And how do I know which of these instructions I need to look up? Well, what you can do is I really like using SharpLab and also godbolt.org for doing this. And so at SharpLab, what you can do is you can take your code, paste it over here on the left, and then you can say, hey, do I want to see the C# version of it, the IL version, or the JIT assembly? And so if we wanted to, we could come and see what this would look like if the F# was turned into IL and then turned back into C#. That might be interesting to you. I'm not super interested in it. IL is super useful because you can see what IL instructions your code is actually turning into. And so you can kind of see what this intermediate representation looks like. And you can also look at the JIT assembly, which is kind of my favorite view of the world right now. And so I can look at, I'm now looking at what this method, the add method, what x86 assembly instructions are being emitted to actually perform this work. And so I can say, oh, I have this integer multiply, I have adds, moves, bit shifts. So I can see what this is composed of. Now, part of the reason I really like the godbolt.org version of this tool, so it's just godbolt.org, and you can choose F#, and this is the exact same thing, but on the right, and this tick here, this back tick is kind of throwing off their formatting, but what's cool is when you hover over these instructions, it's going to give you a description of, hey, this decrements the stack pointer, then stores resource operands, and you can also right-click and say, view assembly documentation, and it will provide you even more information about what these x86 instructions are doing. So this is how I know which instructions I need to go look up the latency for and say like, hey, how fast are those instructions? So I'll provide links to these in the description so you can go and check these out yourself and explore. But what's important is that we're working with integers. So I'm in the integer table here. So integer instructions. And if I look at the arithmetic instructions, and I look at multiply, well, let's look at divide, right? So division, integer division, and let me get these columns here for you just so you know what I'm looking at. I wish he repeated them on different. So how many ops does that instruction take up? The latency, and the latency is important because it's like, how long does this, how many CPU cycles does this take before it's available for another thing to use that result? And I'm not going to go into reciprocal throughput. There's some great descriptions in here about what these things represent, but latency is the one I'm really caring about at the moment. And the latency, like division is absolutely terrible. Like if you can avoid dividing, please do. Multiply is much better, but still, oh, just a sec. Oh. Yeah, latency. Okay, cool. Again, I wish this column is latency. I wish it repeated on each page. So latency on division is absolutely terrible. Multiply is still better, but if we come down to these shifts, bit shifting is insanely fast. Bit shifting is a single instruction and it's available immediately for the next thing. So that's why in our code, and let me switch back here, we much prefer bit shifts to multiplication. And the reason this works is because we're trying to map a number down into unsigned N64s, which are made of 64 bits. So we're needing to divide by 64 to figure out which bucket. And instead of actually doing division, instead of actually dividing by 64, we're doing a bit shift to the right of 6, which is equivalent to dividing by 64 in base 2. And then for the offset, instead of doing the subtraction, we are just masking off like, hey, the offset is just the first, it's just the last 6 bits of location. And again, this is a single instruction with a latency of 1. So again, insanely fast. And then to get the mask, which allows us to say like, hey, give me a mask which identifies the position of the bit that I'm interested in. Again, that's just a bit shift. So bit shifting, if you can do that, and masking is insanely fast compared to multiplication and division. So when you can, and you often can when you're dealing in base 2, and there's things that you can do to make your problem kind of fit into this domain, this is going to be insanely faster. Well, not insanely faster, but I mean, it adds up. So all these little things lead to much better performance, and that's borne out in the benchmarks. So the combination of the inlining, the smarter comparisons, so that you're only doing a single comparison instead of multiple comparisons, and the fact that you're utilizing bit shifting and masking instead of actually having to do division and multiplication is what leads to these additional performance gains. So I know this was way deep. I'm gonna come back to higher level stuff in the next video, which will be fun. But I thought this was it warranted its own video, because I think these are the things that I thought I had something pretty slick at this point, but clearly there was just another level that could be attained. And I really appreciate Mårten for taking the time to do that. And it was really fun just kind of digging through like, okay, what exactly are these things and why do they affect performance? So this was really fun. So I hope you enjoyed it. If you have any more questions, please feel free to leave a comment or hit me up on Twitter. I really enjoy this, and I love sharing what I'm learning. So until next time, you have a great day and keep writing that awesome optimized F# code.